Colligative properties. So we talked about different solutions and solubility and how different factors like temperature and pressure can affect the solubility of gases, solids, and liquids. We also talked about freezing point and melting point of different substances. So we know that water will freeze at 0 degrees Celsius, or an ice cube will begin to melt at 0 degrees Celsius. Now, if you have a water solution and you want it to freeze, when you add salt, knowing that salt dissolves into the water, what do you think is going to happen? Do you think that it is going to keep freezing at the same temperature, or that temperature will change? So if you have these salt particles in your water, it's going to interfere with the water molecules coming together, because now you don't just have your water. You now have these sodium and chlorine ions around your water, keeping them from coming together, because when you're going from a liquid to a solid, right, the particles want to get closer and closer together so they can form that really tight, highly attracted structure. So when you're dissolving a salt, those ions are interfering with the solution coming together. Thus, salt lowers the temperature at which saltwater solution can freeze. A saltwater solution remains liquid even below 0 degrees Celsius. When salt is added to an ice, in an ice cream maker, for example, an ice-water-salt mixture forms that can reach the temperature about negative 10 degrees Celsius. Then, at that point is when the cream begins to actually freeze. So it's way below 0 because you have this salt in it. Now, this depression of the regular freezing point, since we know freezing point of water is known, it's 0. But since we're adding the substance salt in it, it's causing the freezing point to be lower than 0. That depression of the freezing point is something called the colligative property, which is what we're going to be talking about in the next chunk of the chapter. And just a formal definition of a colligative property, it's a property that depends on the number of particles dissolved in solution and not on the type of particle. So it doesn't matter that I added salt. That's not what changed it. It's the fact that salt dissolved in the water, and that's what kept the water from coming together, changing it, the freezing point. So 3 colligative properties we'll be talking about: vapor pressure lowering, freezing point depression, and boiling point elevation. So we already kind of started our talk of freezing point depression. Now let's think of vapor pressure lowering, meaning that the vapor pressure of a solution is going to be lower than what it would be by itself. Now, what is the vapor pressure again? Give me a formal definition. It's the pressure above the liquid when you have gas and liquid in dynamic equilibrium. Now remember, you have this flask, right? And you have your liquid solution, and then you have some of these gas particles above. So when the gas and liquid are in equilibrium, this pressure above it is your vapor pressure. So it's the vapor pressure of a liquid is the pressure of the gas above the liquid when the two are in dynamic equilibrium. So as your liquid is boiling and the gas forms and the gas condenses back to the liquid, they're happening at the same time. That gas that forms above the liquid is its vapor pressure. Now, when you are adding in, so if this was water and I knew my vapor pressure of water and then I added in a salt again, I'm going to interfere with the liquid. So again, the vapor pressure happens because gas particles are forming. If I add in salt, I'm going to keep molecules from getting into the gas phase a lot longer. Thus, the vapor pressure of a solution is lower than that of a pure solvent. We know that in a dynamic equilibrium, the rate of vaporization is equal to the rate of condensation. When a non-volatile solute is added, so now let's take a step back from chapter 11. What does non-volatile mean? Not easily vaporized, right? And then volatile is easily vaporized. So if we're adding in something that's not vaporized easy, like an ionic compound, the solute particles, like sodium chloride, will break up into sodium ion and chlorine ion and interfere with the ability of the water to vaporize because they're basically going to be in the way. So then the rate of that vaporization is going to be diminished compared to just what it would be when it was water alone. The result is continuing. So think of like if you have a concentration solution. So a concentrated solution, I always like to think of like a thirsty solution. It has a really, really strong ability to draw water into it. Like a saltwater solution, because there's so much salt, the salt is going to continually be hydrated. Now, when placing a concentrated solution that has a non-volatile solute in a beaker of a pure solvent in a sealed container, what's going to happen, so if you have this really concentrated saltwater solution and then a just regular water solution, and you place them in a sealed container, over time, the levels of the pure solvent will drop and the level of the solution will rise as molecules vaporize out of the pure solvent and condense into the solution. They will mix. The net transfer of solvent from the beaker containing the pure solvent to the one of the solution shows that the vapor pressure of the solution is lower. So our concentrated solution will draw more of the water molecules to itself because it's really thirsty, lowering its vapor pressure because it does not condense nearly as fast as the water by itself. So before dynamic equilibrium can be reached, the pressure exceeds the vapor pressure of the solution, causing molecules to condense into the solution. Thus, molecules constantly vaporize from the pure solvent, but the pure solvent's vapor pressure is never reached because molecules are constantly condensing in solution. So the reason the vapor pressure is lower is because the gas particles that are formed from these concentrated solutions are constantly being condensed back. And that rate of condensing is really fast that you can't really reach dynamic equilibrium, lowering the vapor pressure of the gas that's above the liquid. The result is a continuous transfer of solvent molecules from the solvent to the solution. We quantify the relationship between the pressure of solution and vapor pressure of the solvent through something called Raoult's law. So you have the pressure of your solution times this is your mole fraction of solvent. We know how to solve mole fraction, and vapor pressure of solvent. So we've already seen this in our ideal gas law chapter. Now, the vapor pressure of a solution is directly proportional to the amount of solvent in the solution. If you have more, it's going to affect how the vapor pressure is lowered. Now, we call vapor pressure lowering as a change in the pressure. So, vapor pressure lowering is defined as a change in pressure from the vapor pressure of the solvent minus the pressure of the solution. That gives us how much the vapor pressure lowered. Again, because the vapor pressure of the solution is lower than that of the solvent. So for a two-component solution, we can substitute the mole fraction of a solvent and find that the change in pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the solvent. The lowering of vapor pressure is directly proportional to the mole fraction of the solute. So some solutions contain volatile solvent and solute. Both can contribute to the overall vapor pressure of the solution. Now, if we think of an ideal solution, the solute and solvent interactions are similar in magnitude, right, to the solute-solute interactions and how the solvent-solvent interacts. When we think ideal, we say that it's polar and polar. The way everything is interacting is the same, so they can actually mix together. So a solute will simply dilute to the solvent, and ideal behavior is observed. So we have the pressure total times plus the two partial pressures, again, where we can find the partial pressure from the mole fraction and the pressure of its substance at its vapor. Stuff we've already seen. Now, what about a non-ideal solution? What do you think, if an ideal solution is that all the interactions are very similar, which is what we want, what would a non-ideal solution consist of? Well, it would be if the interactions are not as good, meaning what if your solute was super attracted toward each other, but the solvent was weak? Well, then the solute isn't going to really break apart, and the solute and solvent don't want to be together. or vice versa. So in a non-ideal solution, the solute and solvent interactions are either stronger or weaker than the solvent-solvent interactions by themselves. Again, you want to make a solution, so you want solute and solvent to be favorable. And if those are not favorable compared to what solvent and solvent is, they're not going to mix ideally. Now, if they are stronger, the solute tends to prevent the solvent from vaporizing, So basically, if the solute and solvent is stronger, right, they're going to be really, really attracted towards each other, like sodium and water, sodium chloride and water, because that's an ion-dipole interaction, stronger than the hydrogen bonding of water. It's going to keep the water from vaporizing. The vapor pressure of the solution will be less than the predicted by Raoult's law if it's stronger. Now, if they are weaker, so if you think of a hydrocarbon like hexane in water, now that's dispersion compared to hydrogen bonding, so the solute and solvent is not going to really be together, so they're weaker. What will happen is that the solute tends to allow more vaporization to occur because the water is stronger than the weaker solute forces. This will then be a greater value of the vapor pressure than predicted by Raoult's law. A solution contains naphthalene dissolved in hexane at a concentration of 12.35% naphthalene by mass. Calculate the vapor pressure at 25 degrees Celsius of hexane above the solution. The vapor pressure of pure hexane at 25 degrees Celsius is 151 torr. Okay, so we have a solution that has our naphthalene and our hexane. And the solution has a concentration of 12.35% by mass naphthalene, which means that I have 12.35 grams, since I can assume 100 grams since I'm given my percent. You want to calculate the vapor pressure at 25 degrees Celsius of hexane above the solution. The vapor pressure of pure hexane at 25 degrees Celsius is 151 torr. So you're looking for the pressure of the solution of hexane, which means that we can use its mole fraction times its vapor pressure. Okay, well, how will I solve for the mole fraction? I know that mole fraction of hexane is equal to the moles of hexane over moles total. Well, do I have enough information to find the moles? Well, I know that moles total is going to be the moles of the hexane plus the moles of the naphthalene. Do I have what I need? Well, I'm given my mass of naphthalene. Can I find my moles from that? Yes. So if you say 12.35 grams divide by the molar mass, you can find your moles. So let's calculate the molar mass. We have 10 carbons, 10 times 12.01 plus 8 hydrogens. I have 128 over 0.164 grams. So 12.35 divided by 128.164, is 0.096 moles. So how about hexane? Can I find hexane? Well, I assumed 100, so I know that if I have 12.35 of my naphthalene, that means 100 minus that amount gives me 87.65 grams of hexane. So therefore, 87.65 grams hexane divided by its molar mass will give me the moles that I need. So 6 times 12.01 plus 14 times 1.008 is 86.172. And that is equal to 1.017 moles. So then you can say, okay, well, my mole fraction is going to be 1.017 moles divided by my total, 1.017 plus 0.096 moles. Your moles cancel because it's a fraction, and you get 0.91. Okay, so now that you have your vapor pressure, your mole fraction, do you have enough to solve for the pressure of hexane above the solution? Yes, because you're given the vapor pressure at that temperature of pure hexane. So then the pressure of the solution of hexane will be 0.91 times the vapor pressure. It doesn't indicate that there needs to be any unit change, so I'm leaving it as torr. And I get 137.996, which I'm going to round to 3 sig figs, 138 torr. Now, before we move on, let's conceptually think if this answer makes sense. Now, my vapor pressure of my pure hexane was 151 torr. Now, my vapor pressure of my solution, so the pressure of hexane above the solution, is 138. It's lower. So that means that the pressure of the solution was lower than that of pure hexane, which does conceptually make sense due to adding in a mixture lowers the vapor pressure. So the naphthalene solution inhibits hexane from being able to vaporize at 151 and lowers it to 138. Okay. Now here you can kind of visualize through the graph the differences when you have the vapor pressure lowering. So it can occur at all temperatures. By comparing the phase diagrams that you can see here, think of a pure solvent. So think that this is a phase diagram of pure solvents. And for a solution containing a non-volatile solute, the effect of the vapor pressure lowering over a range of temperatures can be seen here. Melting going into the left direction and boiling going to the right. So the vapor pressure of the solution is shifted downward compared to that of the pure solvent. The vapor pressure can intersect, right? So the vapor pressure will be by the gas. It can intersect with the solid gas curve at a lower temperature. So the net effect is that the solution has a lower melting point and a higher boiling point, which brings us up to freezing point depression and boiling point elevation. Now, going back to the example I used at the beginning where we know that water will begin to freeze if we are at 0 degrees Celsius, but if you add salt, for example, it interferes. So this is the same exact thing. So you're thinking that we already learned, if we go back to our little graph here, the vapor pressure lowering occurs at all different types of temperatures. And we can see the effect of the vapor pressure lowering over a range of temperatures by looking at the phase diagram of a pure solvent containing a non-volatile solute. So a non-volatile solute lowers the vapor pressure of a solution, resulting in a lower freezing point and an elevated boiling point. The blue is your pure solvent and the red is your solution. Know how the red is more elevated at the boiling and lower at the freezing. So notice that the vapor pressure of the solution is shifted downward compared to that of the pure solvent. And the vapor pressure curve intersects the solid gas curve at a lower temperature. This means that we need lower temperatures to melt and higher to boil. The freezing point of a solution containing a non-volatile solute is lower than the freezing point of the pure solvent. Therefore, the change in freezing point will be the freezing point of the solvent minus the freezing point of solution to give us the change of freezing points, our freezing point depression, delta T, but make sure you have that F. This means freezing point depression, not just change in temperature. This is equal to the molality of the solution times the freezing point depression constant, which is a constant for different substances and can be looked up. The boiling point of a solution containing a non-volatile solute is higher. So again, if you have sodium chloride in water and you're trying to boil it, those ions are going to interfere with the gas particles at the surface escaping. That's why the vapor pressure is lower, which then keeps them from escaping into the gas phase, needing higher temperatures to do so. So the boiling point is elevated. So then the change in boiling point, the boiling point elevation, is equal to the boiling point of the solution minus solvent, notice how it's flipped, is equal to the molality of the solution and the boiling point constant. Best way to interpret these is through a problem. So calculate the freezing and boiling point of a solution containing 1 gram of naphthalene in 100 milliliters of benzene. Benzene has a density of 0.877 grams per centimeter cubed. So you always have to think, what is my solute, what is my solvent, what is my solution? So you want to know the freezing point and the melting point of the solution that has 1 gram of naphthalene in 100 milliliters of benzene. So your 1 gram of your naphthalene is your solute, and the 100 milliliters of benzene is your solvent. So the two together is your solution. And you want to know the freezing point and boiling point of this solution. Okay, so I know that to find my elevation and my depression, I need my molality and my constants. Well, I can find my molality. My molality is the moles of my solute over the kilograms of my solvent. All right, well, let's try this here. So to get my moles of my solute, do I have enough information? Yes, I have my mass, so I can find my moles by dividing by the molar mass. So I already forgot, we just did this, but what was my molar mass of naphthalene? 10 times 12.01 plus, not minus, plus 8 times 1.008 is 128.164 grams. That gives me 0.0078 moles. Now I want my kilograms of solvent. Well, I have volume. Do I have enough information to get the kilograms of benzene? Well, I'm given density of benzene. I usually know if I have volume and density, I can find mass. But what's weirding me out is the fact that I have milliliters here and centimeters cubed here. Can I relate the two, or do I have to do some conversion first? Well, 1 milliliter is equal to 1 centimeter cubed. Therefore, 0.877 grams per centimeter cubed is equivalent to 0.877 grams per milliliter. So then if I take my 100 milliliters and multiply by my density, I can find my mass. And I get 87.7 grams. However, for molality, I want kilograms. So then I have to do one more conversion and divide by 1,000 to get my kilogram of solvent. which gives me 0.0877 kilograms. Now I have enough information to solve for my molality. Moles of solute, 0.0078, divided by kilogram of solvent. What does that come out to be? 0.088. Oopsies. That is very thick. Now this gives us mole per kilogram. The units don't cancel, which we don't want. So we can abbreviate to saying 0.0889 m, where little m stands for molality. Okay, so I just solved for my molality. Now what can I do next? Well, I want to know the freezing point and boiling point of the solution, so I don't want to know change exactly yet. But first, I'm going to solve for the change. So if I plug in my molality, 0.087, nope, that was wrong. 0.0889 m times my, what do I need? I need my freezing point constant. So I have to look up my freezing point constant of naphthalene, which is, I need to look up freezing point constant and boiling point constant. My freezing point constant of naphthalene is negative 6.94. So just positive actually. So 6.94. So I multiply it by 6.94 degrees Celsius over molality, which is equal to, now again, the freezing point constant, that's what you look up. So you get 0.0889 times 6.94. That's equal to 0.6169 degrees Celsius. And then we can do the same thing for the boiling point elevation. Now, something I want to point out. We just solved for the freezing point depression. We just actually here solved for delta TF. Is that what we wanted? No, you want freezing point of solution. So I'm going to erase my work here. And before we move on to the boiling point of the elevation, if I want the freezing point of solution, I know that the freezing point of solution is equal to coming from the depression. So freezing point depression is equal to freezing point of solvent minus freezing point of solution. And the freezing point of the solution is what I'm solving for. So I need to know what the freezing point of the solvent is. Well, that means I need to look up the freezing point of the solvent. And I just realized my error. So I didn't need to actually use the KF of naphthalene. Now remember, you're using the molality of the solution and the constant of the solvent. And I used the constant of the solute. So there's a little error there. Glad I caught that. So here's where everything gets tricky because you constantly have to remember all of your constant. What is my solvent? My solvent is benzene. Well, if I look it up, my actual freezing point constant of benzene is 5.12. Now again, I did this because I forgot that I need to use the solvent, not the solute. So you look up the freezing point constant of the solvent. So then depression changes, so 0.0889 times 5.12, so we get 0.455 as the freezing point depression. So if I have 0.455 degrees Celsius and I want to know the freezing point of my solution, what else do I need to look up? Freezing point of the solvent. Now again, little error, fixed it. We needed to know the constant of the solvent, which we did, and this gives us the freezing point of the entire solution. Now, that gives us the depression of the entire reaction. We are trying to find the freezing point of the solution, so I have to look up my freezing point of benzene, which is known, and that is 5.5. So now what would be my freezing point of my solution? So if you take your 0.455 minus 5.5, then you'll have a negative and divide by -1. And you get 5.045. Now, before moving on, does this conceptually make sense? Well, the freezing point of benzene is 5.5, and the freezing point of the solution was 5.045, so it is lower, so that makes conceptually sense because the freezing point of the solution should be lower than that of the solvent. Okay, so now let's try it for our boiling point. So now we already have our molality, and we need to use the boiling point constant to solve for the boiling point elevation. Now, again, not making the same mistake twice, I'm looking for the boiling point constant of the benzene, which is 2.53. Now, for those of you that are wondering where I'm getting these numbers from, this is on page 601 in your textbook. So if I multiply these two together, 2.53 times 0.0889, I get 0.2249. Now again, this is my delta TB, right? This is my elevation. Well, if I remember correctly, the elevated temperature comes from the boiling point of solution minus boiling point of solvent. So I solved for my elevation. So I need the solution, that's what I'm solving for. So I have to figure out the solvent. So I have to look it up. Well, the boiling point of benzene is 80.1 degrees Celsius. So then my boiling point of my solution will be plus 80.1, 80.32. Now, does this conceptually make sense? Yes, the boiling point of the solution is a little bit higher than the boiling point of elevation. Now, again, it doesn't have to be a significant change, but it is elevated from what it was on its own. All right, last colligative property is osmotic pressure. So the process by which seawater causes dehydration is osmosis, right? We already talked about how when you have a beaker with water and then a beaker with really, really salty water, the salt water is going to continually take water molecules from the just regular solvent. That is called osmosis. Osmosis is the flow of solvent from a solution of lower solute concentration to one of higher solute concentration. Concentrated solutions draw solvent from more dilute solutions because of nature's tendency to mix. So you have very, very salty water. It continually wants to become, it's very, very thirsty. It's really concentrated. So it's really dehydrated. So it constantly will pull from a more dilute solution to kind of help itself out. Now, before I talk about these two bullet points, the best way to talk about them is through our diagram. So here we're illustrating an osmotic cell. So the left side of the cell contains a concentrated seawater solution, and on the right side of the cell we have pure water. Notice here how we just very, very concentrated pure water. A semi-permeable membrane is a membrane that selectively allows substances to pass through. but selectively, right? Allows substances to pass through selectively, so not everybody can go. It separates the two halves of the cell. So water flows by osmosis from the pure water side of the cell through the semi-permeable membrane and into the salt water. So here we have the pure water. They want to help dilute the salt water that's super concentrated, so it flows through the semi-permeable membrane into the more concentrated side. Over time, the water level on the left side will rise. So if you're constantly going from this side over, from the left to the right, over time you'll have less water on your left and more on your right. The water level on the right side will fall as the left will rise. So if external pressure is applied, because they're open to the atmosphere and we always have pressure coming down on us, if the external pressure is applied to the water in the left side, the process can be opposed and even reversed. The pressure required to stop osmotic flow, so if I open this to pressure and I'm pressing down, it can actually cause the process of osmosis to stop. And that pressure required to stop osmotic flow is called osmotic pressure, which is equal to the molarity, the concentration of the solution, your R constant times your temperature. So again, because we're applying an external pressure, what you are doing is you're opposing, due to pressure, the amount of water that can flow to actually reverse the process of osmosis. So we call that osmotic pressure, the pressure needed to stop osmosis. So we know water flows by osmosis from the pure water side through semi-permeable membrane into the saltwater side. And over time, the water levels are different. And now if we apply an external pressure, we then can reverse and stop the process, and that pressure is our osmotic pressure. A solution containing 27.55 milligrams of an unknown protein per 25 milliliters of solution was found to have an osmotic pressure of 3.22 torr at 25 degrees Celsius. What is the molar mass of this compound? So you have a solution that has 27.55 milligrams. You have 25 milliliters of the solution. You have the osmotic pressure at 3.22 torr, and you have a temperature of 25 degrees Celsius. And you want molar mass. So you want grams per mole of the compounds. So of the solution. Well, you have the grams part because you can convert milligrams to grams. There's 1,000 milligrams in a gram, so 27.55 divided by 1,000 is equal to 0.02755 grams. How can I find the moles? Well, I'm given my osmotic pressure. What is the definition of my osmotic pressure? It is equal to the molarity times R times T. Well, I'm given my temperature. I always know R. I know my osmotic pressure. Okay, well, that means if I isolate molarity, I get osmotic pressure RT. Well, I know molarity is equal to what units? Mole over liter. There's that moles I'm looking for. All right, so I kind of have a process now. Since I'm giving my pressure, my R constant, my temperature, I can isolate for molarity. So I'm going to do that first. Well, what R am I going to use? Since I have torr, I'm going to use 0.08206 liters atmospheres over mole Kelvin. So what do I have to do first before plugging it in? Or you can plug it in together, but what do I need to be aware of? You have to convert your units. So 3.22 torr divided by 760 torr to give you an atmosphere. Divided by 0.08206 liters atmospheres mole Kelvin times your temperature. Now your temperature also has to be in Kelvin. Awesome. From there you can solve for your molarity. So 3.22 divided by 760. You divide that by 0.08206 times 298. That's equal to 1.7232 times 10 to the negative fourth molarity. Okay, so I have 1.732 times 10 to the negative fourth moles over liters, and I want moles. How can I get that? Well, I have my milliliter of solution, so if I multiply this by my liters, what's 25 milliliters in liters? Well, divided by 1,000, you get your liters. 0.025 liters gives you 4.33 times 10 to the negative 6 moles. Now, to find your molar mass, you take your 0.0255 grams, divide by your moles, 4.33 times 10 to the negative 6 moles. And what do we get? Very, very high molar mass, 5889.145 grams per mole. Now, as your engagement question, the last one for the day, I want you to go through this and check if there's any mistakes. Does this answer make sense? Were the conversions correct? If so, explain. And if not, explain otherwise. So double check your work and explain to me how you worked through this problem with me